Let's discuss some questions from the 2023 exam network section. Question 12 gives you 5 states and the edges between the vertices represents borders between the states. So what's the sum of the degrees? Now sum of the degrees is equal to 2 times the number of edges. Some students of course write down the degree, that means the number of edges going out from every vertex at each vertex, and then add them. I, on the other hand, always use 2 times the number of edges. Now, if you count the number of edges, 1, 2, 3, 4, 5, 6, and 7, there are 7 edges in this diagram, or in other words, graph, and therefore 2 times 7 is 14. Now, Euler's formula is V plus F is equal to E plus 2, and Euler's formula is usually associated with connected and planar graphs, okay? So, a single edge connecting all the vertices and no multiple edges in between. Now complete the formula by writing down the appropriate numbers. So we know that there are 5 vertices because that's the number of states. We also calculated the number of edges in the previous question as 7, and the number of faces is equal to 1, 2, 3 and the face outside. And so we see that it adds up to 9 on both sides. So as I mentioned previously, Euler's formula holds for this graph because the graph is connected and planar. So when you see Euler's formula, it should connect you to these 2 words. Let's look at the next question. The diagram below shows the position of state A on a map of this country. The 4 states are indicated as 1, 2, 3, 4. Please don't look at this. These may not be correct. So I've redrawn this diagram so that I can make connections, and I have written the degree of every vertex next to it, okay? And I think that really helps. So the first thing I look at is, now A's position is here, and A has, the degree of A is the number of connections it makes. So 1 and 2. So clearly we can see the degree is 2 over here. Now let's look at 2. Now 2 has 1, 2, 3 and 4. So clearly over here that must be C. Okay. Now let me choose another color. Let's look at 3. Now 3 makes connections 1, 2 and 3. Now 3 could either be B or D, so we leave that alone for the time being. And let's look at 4. 4 has connections with, I think I'll do it with another color. 4 has 1, 2 and 3. So both these 3 and 4, so it could be B or D, okay? B or D. Now that's not really helping me, is it? So what I'll do is I'll look at 1. Now 1 has 1, 2 connections, okay? So that tells me that 1 is E. And E has connections with C and D. So if E has connections with C and D, that we've already got C over here in the diagram, so that implies this must be D. And if that is D, the only alphabet that we have left which we haven't got is B, and B is also 3, and that is B. So finding the degree of the vertices and matching them up to your graph is the easiest way. I've experimented with a few ways, and this is the easiest way to do it. So if you write that down, so B is 3, C is 2, D is 4, and E is 1. There are different ways of doing it. You don't have to follow my method, whatever works for you. It just depends on how you think about things, okay? Now question 13 talks about 9 landmarks given, and the edges on the graph represent the roads between the landmarks, and the values on those edges represent the length in kilometers. And the very first question says 3 friends, Eden, Reynolds, and Sheila, meet at landmark G. And question A says Eden would like to visit landmark M. What's a minimum distance? Now I know I can do this through Dijkstra's algorithm, but it takes too much time to work backwards from M. So what you do is you lay down some of the obvious paths, okay? So one of them is the direct one, and another one is that one. Another one could be that one, and another one could be that one. And so if you lay down these 4, they're not too many, okay? The least value is 5.9. The second question says Reynolds would like to visit all the landmarks and return to G. Very important. Now they all start off from landmark G. So when you visit a landmark, visit every vertex and return to the same place you started, it's called the Hamiltonian cycle. Okay, so in order to visit every vertex once, you need not visit every edge. That's something you should remember with the Hamiltonian cycle. Okay, it's also called the traveling salesman problem. Now, if you look at the diagram, the easiest way that you could do that is, so what I did was I went along here. It's a bit of, there's no particular rule to this, as long as you visit every edge and you don't have to revisit a particular vertex, okay? So one of the paths is that one, or you could also have the reverse path. So in a Hamiltonian cycle, okay, if there's a path forward, there's also a path backwards. Part C says Sheila would like to travel along all the roads, which means all the edges. To complete this journey in the minimum distance, she will travel along 2 roads twice. Now, when the question ever talks about traveling along 2 edges or any edge twice, okay, you always connect it to the degrees of the vertices. Sheila will leave from landmark G, but end at a different landmark, okay? So if you are talking about the degrees of a vertices, you are talking about the Eulerian trail. So if you start at one but end at another, then you should be looking at odd degree vertices. The 2 roads that will be traveled along twice are the roads between. You should look for odd degree vertices like I've indicated. Now, if you leave the one which is the starting value, okay, the starting point. So I've indicated on the diagram all the odd degree vertices. Now, there are 2 edges from the starting point, H, GH and GN. Now, H does not connect to another odd vertex, so leave this, okay? Now, if you look at N does connect to L, both are odd degree vertices. And if you look at the other odd degree edge with vertices with odd degrees, it is JM. So, looking back at the question, if you have to travel along all the roads, and in order to complete this journey, she will travel along along 2 roads twice. Okay, she will leave at landmark G but end at a different landmark. So you complete these 2 boxes. So for an Eulerian trail to exist, what you should remember is that you have to have exactly 2 odd degree vertices. Exactly 2 odd degree vertices. If you don't, you have to travel along some edges twice. And the way to do it is to look for edges with odd degrees in them, okay? Otherwise, it is not possible to leave landmark G and end at a different landmark. which would only be an Eulerian trail. So these are the two edges which have to be repeated.